Lesson 10.4, page 568, inverse of a function. In this lesson, you will learn how to find the inverse of a relation. You will explore inverses of functions. You will find inverses of functions algebraically. Remember, algebraically means by showing work. And then find inverses of nonlinear functions. So I guess we got to know what an inverse is in the first place. Let's talk about finding the inverse of a relation. So recall, a relation is just inputs and outputs. Maybe we should review a function right now too. Remember, a function means each input only gives me one output. That's a little different than a relation. A relation is just a table of inputs and outputs. Now, an inverse relation switches the input and output values. So in other words, if you switch x and y around, you just created the inverse of a relation, which is what this is showing you right here, okay? This inverse, just switch x and y around. Might be easier to show an example. Look at these examples here. This first example, I want to find the inverse of the relation. So look what they do. They switch the x's and y's around. So the inverse of these ordered pairs would be 7, -4, 4, -2, 1, 0, -2, 2, and -5, 4. They just switch the x's and y's around. Look at these tables. Okay, here's an original table. If I switch x and y around, as you can see here, I just created an inverse relation. So instead of having -1 for the input and 5 for the output, I'll switch it to 5 for the input and -1 for the output, and so on. That's how you find the inverse of a relation. Real simple to do. What I'd like you to do is pause the video and try 1 and 2. I want you to find the inverses of these relations. And you're back. And I didn't write out all of number 1. I think you get the idea. To find the inverse of this, you just rewrite it as -4, -3, 0, -2, 4, -1, etc. Okay? And then for the table, if I just take the outputs and write them as inputs, and I take the inputs and write them as outputs, I just created an inverse relation. So there's my table. Okay? Now, what does this inverse of functions do, or what does it mean? Throughout the book, you have given inputs to find corresponding outputs of y equals f of x for various types of functions. So it's important to remember, you know, all throughout the book, the inputs were the x's and the outputs were the y's. When you do inverses, you're going to flip those around, okay? You've also used outputs to find inputs. So if you knew y, you could figure out x, is what that's saying. Now you will solve equations of the form y equals f of x for x to obtain a formula for finding the input given a specific output. So in other words, this is a fancy way of saying if you solve for x, you will rewrite your equation as an inverse. Okay, so if you're like, that sounds confusing, it's not. Look at this example. This shows it really easily. Okay? Let f of x equals 2x plus 1. Solve y equals f of x for x, and then find the input when the output's -3. So they're saying, okay, this is like having y equals 2x plus 1, so that's what they wrote. Solve for x. So let's solve for x. Take away 1 from each side. Now y minus 1 would equal 2x. Now divide by 2 on each side. X equals y minus 1 over 2. You just wrote the inverse of the function. Okay? Find the input, find x when y is -3. Well, that's easy now. Take -3 and plug it in where you see y. So -3 minus 1 on top divided by 2 would give me x. That's -4 over 2. X is -2. So if the output's -3, the input must have been -2. To find the inverse, you just have to solve for x. Why don't you pause the video and try 3, 4, and 5. I want you to solve these equations for x and then find the input when the output is 4. Go ahead and do that. And we're back. So here's question 3. I'm solving for x. I added 6. X equals y plus 6. I then plugged in 4 for y, and x must have been 10. And you can see my work here for 4. And there's my inverse equation and my answer for x when y is 4. And here was my number 5. If you have questions about those, make sure you ask about it in class. Now, in this last example, do you notice the steps involved after substituting x in for y equals 2x plus 1 and after substituting y in for x equals y minus 1 equals 2? They are inverses, okay? So if you're like, I don't get what that says, okay, look here. Look at what I'm pointing at right here. If we solve this equation for x, we have to do 2 steps. We have to subtract 1 from each side first, and then we have to divide by 2, and I get this equation. If I wanted to solve that equation for y, it would take 2 steps. I'd have to multiply both sides by 2 first, and then add 1. Do you notice how these 2 equations, it's the complete reverse order of operations to get from one to the other? Okay? So what I'm trying to tell you is that these steps undo each other. These are then called inverse functions. They're functions that undo each other. So that's what an inverse function is. These 2 equations would undo each other, basically, because their steps to solve are in completely the reverse and inverse order. So you can see the original function, we could write f of x equals 2x plus 1. And the inverse function, this one, we could write it as g of x equals, I'll put x back here, x minus 1 over 2. That would be the inverse function. So these 2 functions are basically, they undo each other. They're called inverse functions. Because an inverse function interchanges the input and output values of the original function, the domain and range are also interchanged. So they're just saying, for my original function, the domain for this would be the range on this one, and the range on this function would become the domain of this one. They are interchanged. They graph both of these, and you can see the graphs here. Do you notice these 2 graphs mirror each other over a diagonal from the lower left of the graph to the upper right? Let me highlight that diagonal. It's right here. Okay? Inverse functions always mirror each other over that diagonal. For example, let me highlight some points. Do you notice this point on the original function? This is one of the points for this function here. Do you notice how if I go over here, there's the mirrored point on this function? Or look at this point. You see how it's about 1 diagonal away? If you go 1 diagonal away, there's the mirror. Or if you go 1.5, there's 1.5. Okay? Inverse functions always mirror each other over the diagonal that goes from bottom left of the graph to the upper right. Let's show how you can find the inverse of a function algebraically. It's easy. 3 easy steps. The first step, make f of x y. So we have y instead of f of x. Then switch the x and y in the equation around, and then solve for y. And you're like, I don't get that, okay? Let's do this one together, and I think you'll see it's easy to do. So find the inverse. I want to find the inverse function of this equation. So I'm going to write down, first of all, y equals 4x minus 9. Okay, there's step 1. Step 2, switch the x and y around. Put x here and put y here. There's step 2. Now solve for y. So I'm going to add 9 first. So x plus 9 would equal 4y, and then I'll divide by 4, and y would equal x plus 9 divided by 4. And since they want a function, I'm going to use function notation. Instead of calling it y, I'll call it g of x. G of x would equal x plus 9 over 4. So this is the inverse function. So the original function was f of x equals 4x minus 9. Here's the inverse. I'll write the word inverse next to that. The inverse of that function would be x plus 9 over 4 equals g of x. And if I graph both of those, do you notice how these two graphs mirror each other over that diagonal horizontal line again? Let me highlight that diagonal line here. These two functions mirror each other over that diagonal line. What I'd like you to do is pause the video and try 6 and 7. They ask you to find the inverse of the function and then graph the function and its inverse. Okay, and here's 6. This is a good review, really, of slope-intercept form, actually. So here's my function, f of x equals 6x. Let's think for a minute. That's like saying y equals 6x plus 0. So let's do a little review there. This is actually excellent review. Okay. My slope is 6, my y-intercept is 0. So you notice here's my y-intercept and my slope. Up 6 over 1, up 6 over 1. Okay, there's the function f of x. Now I need to find the inverse function. So I start off by writing y equals 6x, flip the x and y around, so now I have x equals 6y. Solve for y, divide each side by 6, and y equals x over 6. Now this is in slope-intercept forms. Okay, maybe I should write this down. This is saying I have y equals 1/6 x plus 0. So my y-intercept is 0 and my slope is 1/6. So let me graph that. So there's my y-intercept 0, up 1 over 6. And now I want to show you, if I take my diagonal line and draw it again, here's my diagonal. Do you notice how these two lines mirror each other? Okay, over that diagonal line. So let's count. From here, it's 1, 2.5 spaces. So look at 1, 2.5. These points will mirror each other over that diagonal. Okay, inverse functions always mirror each other over that diagonal from bottom left to upper right on your graph paper. And then here's the next problem that we did. F of x equals negative x plus 5. So I'm going to graph that. My y-intercept's 5, that's here, and my slope is negative 1. That means go down 1 over 1, and I'm doing that. Okay? Let's get the inverse function now. So y equals negative x plus 5. Replace f of x with y. Switch the y and x around. So x equals negative y plus 5. Take away the 5 and divide by negative 1. I get y equals negative x plus 5, so g of x equals negative x plus 5. It's the exact same function. So I'm going to draw the same line. Now let me get out my diagonal real quick, and let's draw that, and you're going to notice these points mirror, so that's what's going on here. Okay, that's why it's one line on top of the other, because on my original function, you know, this point is 1.5 away, and it mirrors, so both of these end up being the same for that. Now, nonlinear functions, we can find the inverses of those as well. The inverse of a linear function is also a function. Now remember, functions mean there's a one input gives one output. Do you remember the vertical line test? You can always tell if a line or a graph is a function if you draw vertical lines and each vertical line would only touch one point. Okay? Now it's important to note though, the inverse of a function is not always a function. Okay? The graph of f of x equals x squared is shown. You see that here. And here's its reflection over the diagonal line. And you notice this reflection, if I start drawing vertical lines, it's going to fail the test. All right? So the inverse would not be a function. However, if I restrict the domain to only positive numbers, then it would be. Okay? So for example, if I just take this graph and I restrict it to only this part where x is positive, I get this picture. Now in this picture, if I draw vertical lines, you notice there's no place where a vertical line would touch either one of these in more than one place. So if we restrict our domain to positives, then the inverses would be both functions. Let's take a look at this question. F of x equals x squared. Find the inverse when x is greater than 0, greater than equals 0. Okay, so again, this is a parabola. So 0, 0, 1, 1, 2, 4, and you can see that here. We're only graphing in the positives. Now the inverse, let me highlight this diagonal, okay? So for example, this point would reflect over here. And we have a point here that would reflect here, and 0, 0, and you can see if I take this point, it's about 1 away, that would reflect here. You see how the inverse is the reflection, and both of these pass the vertical line test. Okay, now, you don't have to draw both of these to determine if the inverse is a function. You can use what's called a horizontal line test. Okay, so you're like, what's a horizontal line test? If the original function passes the horizontal line test, that means its inverse would also be a function. So let's go back to the original function in this problem. It was this parabola that I'm going to highlight or mark in blue, okay? There was the original function right here. Let's do the horizontal line test. Do these lines touch this function in blue in any more than one place? And the answer is no. Okay, it passes the horizontal line test, which means its inverse would also be a function. So you can use the horizontal line test to determine if a function's inverse would also be a function. So that saves you the time of having to always graph both of them. Okay, so let's use the horizontal line test for this question. It says, consider this function and determine if the inverse of that function is a function. So if I graph this, I could just use my calculator, y equals square root x plus 2, hit the graph button, and you'll see this picture. Does this pass the horizontal line test? Let's try, and yep, there's never a time where it touches in more than one place, so it does pass the vertical line test. So the answer is yes, the inverse is also a function. Okay, find the inverse. Well, to find the inverse, it's easy. We just have to quickly write y equals square root x plus 2, change x and y around. Okay, I got to square each side. X squared would equal y plus 2, and if I take away 2 from each side, y would equal x squared minus 2. And then write it in function notation. I'm just going to call it g of x would equal x squared minus 2, and you see that's what they have here. Okay, there's an inverse of the function. What I'd like you to do now is pause the video and try 10 and 11. In 10, they want you to find the inverse of the function and then graph the function and its inverse. So pause the video and do that. And then 11, they ask you, is the inverse of this a function? Then find it. Okay, and here's 10. They want me to graph this for a domain of x greater than or equals 0. So this would be half a parabola opening up. Okay, now the inverse, it's easy. There's my diagonal. If I just mirror these points, and you can see I'm just mirroring 1, 2, and this point would be mirrored over here somewhere. There's the graph of the inverse. I don't even need the equation. I can just mirror it. Okay, let me write the inverse. Okay, replace f of x with y, switch the x and y around, and now solve for y just using onion. Take away 3. Divide by 4, square root each side, and I better add one more thing. Let's rewrite it as g of x equals the square root of x minus 3 over 4. There would be the inverse of the function for 10. And then in 11, let me put that in my calculator real quick and take a look at the graph. So you can see I've entered this in my calculator. I'm going to hit graph. And now let's check on the horizontal line test, and you notice I'm just kind of drawing with my pointer here. This is always going to pass the horizontal line test because there's only one place that my horizontal lines would ever touch this. So yes, my inverse is a function also. And then here was my work to find the inverse. Just write the equation, replace x and y, flip them around, and now solve for y. And I probably should write this in function notation. G of x would equal x squared plus 1 over 2. That's the inverse. I'm going to stop the video here. If you have any questions, make sure you ask in class.